Today we're going to finish up with airports and airplane type things in flight and move into railroads. Another mode we have yet to touch in our introduction to transportation, and that will kind of complete a lot of it. We'll talk a little bit also today about uh, shipping and shipping by water means through that. So to start off with kind of some general things to finish up on the airline piece of it is this last year, one of the students had asked me what the fuel efficiency of an aircraft is and how much fuel does it take a 737 to go from New York to Chicago or somewhere like that. Right, how much fuel is being burned? Well, I didn't know. So we looked it up. And so these are some slides coming from that, just giving a general idea. This is just showing relative fuel efficiency. And zero is just kind of, they picked a normative, I don't know if it's the average value for it. And then if you're on this side, you're using more fuel. And if you're below that line, below the zero line, then your fuel efficiency gets better if you're above, and it's worse if you're down below. Right, and the blue dots are twin engines, and the orange dots or red dots are four-engined planes. All right, so the Boeing 747, we've sent a couple pictures of that. This is where it would land, and it gives you an idea of, and this is by mass of taking off, what its fuel efficiency is. And so 747s are running about 3% less efficient than the average fleet average for that. A330s, they're an older plane too, not as efficient. They weigh less, but they're still lower efficiency in the same range about the 747s, right? The A340s, the A380, that's the double decker, that huge Airbus, which has been discontinued now after only 15 years of manufacture, is much less efficient, and it's a lot heavier. Look at this, all right? So it's got 550 tons plus versus even a 747, which is only 450 tons, right? 450, this is the extended range version. This one's made to go even farther. And by taking longer flights, they're less efficient. Now you're carrying more fuel on board, and you have to have more takeoff weight to go farther like that. And it makes your per seat fuel efficiency less. And this is, I guess, by passenger. So passenger kilometers per liter of fuel. And so these extended range ones, I think that's what the E is here as well, they tend to be less efficient. All right, so here's the 777s, which are the main long distance international planes now. Kind of took the place of what the 747 used to be. Right, so the LRs are the long range, ERs and extended range. Not quite sure what the difference is for that. And so that's the 300 is a little bit larger. Being larger, it's not going to be as efficient as the 200. It's a little shorter plane. So you can see its efficiency goes up. A330s, which are really popular, they're up to a little higher. And then the 787s, when they came in, because they have a lot of carbon fiber fuselage, they weigh less. And one of the reasons they sold so well is that they are more efficient. And that's why they've become really popular. Again, on international routes, they don't hold as many passengers as a 777 does for that. And so you can see that here's an older one. This is from the 80s, 767, 300ER. A lot of flights from Chicago to Heathrow are 767s. That's right in their premier range, I guess, right? But you could save fuel if you were flying a 787, and that means a lot of money to airlines. Well, right now fuel prices are down, but generally they're up, and so saving fuel is a big issue with them per passenger mile or per seat mile. Sometimes they list it either way. This is a little different chart, same kind of idea, and we're plotting the airplane efficiency, and we just set 1968 equal to 100. So whatever 100 here in 1968, that was the average value. And now we're just comparing it over time compared to what the fuel efficiency of an airplane was in 68. We're comparing it over time. This is a STA is a small twin aisle aircraft. So you've got two aisles to walk through in the aircraft, but it's probably a 222 or a 232 set up in seats. And then a single aisle aircraft, this is the 737 and the A321s, would be a single aisle aircraft. And you can see that over time, their fuel efficiency has gotten better and better. All right, through that. And this is fuel burn off of some random value they set it equal to 100 in 1968. So they're burning even less and less fuel. Here's a trend line showing what it is. It was doing really good coming down, and then it kind of flattened out over the last 10 years or so. But some of the new aircraft, small twin aisle ones, are doing even better, right? And so our fuel efficiency is going well. This is what the aim is, that by 2020 this would be the fuel goal, and 2030 that'd be the fuel goal, right? So we would be using, right now we can almost get to half as much fuel being burnt by a plane as it was 1968 average. That's pretty good, right? Some of these, I don't know which aircraft exactly these are, and they don't say, but that's, we're almost at the 50% line right there. So we're burning half the fuel for the same flight. That's a really good improvement. Right? Now, it has been 50 years, but it's still pretty good improvement, right? Jet technology has gotten a lot better than it used to be. I don't know, I wonder what that was, but anyway, some jets really burn a lot forward there. That's the main reason airlines will buy new jets, is to save fuel. Right. The age of the aircraft, if properly maintained, which in the U.S. is very strict rules on maintenance on aircraft from the FAA, and they're inspected and they're checked, and you have to keep logs about everything. That's not so much the problem about age; it's going to be that fuel burn that's what really pushes an airline to switch. And so here's the question that had come up was, well, how much fuel does it take to fly a 737 from wherever to wherever in the U.S.? So this was an interesting one. It took a lot of hunting to find these charts, right? It's not something. It's not like a sticker like on a car, and you're going to buy it. It tells you what the fuel economy is. Right? There's a lot of variables. Keep that in mind, right? A shorter flight can carry less fuel and become more efficient in the burn versus a really long flight. They were last year in the fall, I think they tested a flight from Australia all the way to London direct, and only Melbourne is close enough usually to do it, but they did a Sydney to New York flight as well, and they tried both, and they're like 18-19 hour flights. I mean, super long, and there's no aircraft that can economically do that. Well, one of the problems is, in these test flights, the plane was only half full because they couldn't take a full load of passengers because it's too heavy. They had to have so much fuel on board that they couldn't take that many passengers. So it's not an efficient way. They didn't make any money probably on their test flight. But they wanted to see how the pilots and how the passengers handled a really long flight. And it was somewhere 18 to 20 hours, I think, in the end, on board this plane. But you didn't have to transfer, right? Total trip time is less, but you're just stuck on the plane that long. Anyway, nobody makes an airplane that can go Sydney to New York right now direct with a full passenger load on board. And so they've asked both Boeing and Airbus to make one that could, but nobody can. But anyway, the point is that flying really long distance is less efficient because you're carrying so much fuel, and then you have to carry fuel to transport that extra weight of the fuel. So it becomes kind of a downward spiral when you get to a certain point, right? So keep that in mind. Shorter flights and maybe a mid-range flight is maybe where your max efficiency is going to be. Well, here's the fuel burn. This is what pilots will look at, how many pounds per mile they're on average you're going to burn for that. And of course, it does depend if you've got a headwind or a tailwind and so forth like that. Well, I'm sure they've corrected for all that in here. Here's how many seats they can fly. Well, the seats is important because over here now, this is, I think, the coolest number I found, which is miles per gallon per seat. Right, think about that. All right, so we're used to seeing miles per gallon for a car, right? Well, if you got 110 miles per gallon in your car, you'd be pretty happy, right? My little Focus gets 44 on its best day, and it's usually around 40. I think that's a really good miles per gallon. And I'm driving by myself, right? I could use less fuel if I was flying. That's how efficient modern jets are for it. And some of these aren't that modern. All right, here's the 747-400, right? It was 73 miles per gallon. So that's per seat in the plane. If your plane is full, it's 73 miles per gallon per person, right? Here's the 737 MAX. Ooh, I know, don't mention the MAX. It was getting 110 and 93. The max 737 MAX line, until this last year when they had their wrecks, was the best-selling airplane in aircraft history. Right? Boeing had more orders for those than any other plane before it. And typically these order backlogs last, what, 4 or 5 years, so it was a long order. And this is why, 110 miles per gallon. It had an incredibly good fuel burn. Its main competitor is the A320 and the A321, and the A321neo out there, right? They're at 97. They're matching it, and they're really close, right? And that is why everybody's talking about retiring the 767s. Here's why, right? You're only getting this kind of mileage out of that. Right, and it depends on the configuration, how many seats you've got, just how efficient it is. If you've got all economy, you're probably going to get 224, and then it's more efficient, right, for that. But still, that plane in general is, these fuel burns are very similar on that, and probably the only difference is the weight of how many passengers you have through there. But that's what airlines are looking for. So you can check off this chart and see these older ones. That's why they're retiring them. Like these 72, 73, those are bad numbers. You're going to lose money in the long run for that. It's a fairly tight market in that. Well, here's some interesting stuff that had nothing to do with anything else. But when I was searching that, I found this, which I didn't know, that the length of the seatbelt is different by airline. I just thought there was some standard length. I never really paid attention. Right? So if you're a big guy like me, I'm going to fly Hawaiian from now on, and maybe Aeromexico, because I need a nice big old seatbelt. Look at that. That's over 50 inches long. Right? But I usually fly Delta. That seems to be my number one flight. Where's Delta? Yeah, Delta's okay. Oh, United. I'm going to have to go on a diet if I fly United. All right. There. That was just totally random. It had nothing to do with anything. Here's talking about fuel efficiency, and since we're going to switch now from air and talk about rail and trains, here's an interesting graphic, I thought, which is energy expended per passenger mile. So to move 1 passenger mile, here's how much energy in BTUs is expended to do that. Amtrak, this is probably published by Amtrak. Actually, it's Transportation Energy Data Book. Sure, Amtrak likes to tout this one. Look how efficient they are, right? Trains are really efficient. Your steel wheels on steel rails, there's very little friction there, right? Not like a car tire on a road. And you can move a lot of people with a single locomotive. It is built to be very efficient. And that's why we still have trains, because in certain markets, they're just very efficient at moving things, and keeps them competitive. Even though they have very little federal money involved in them, any tax money, only occasionally do they get some grants for crossing upgrades and things like that. They're all privately owned, and they can still compete with interstates, which are publicly funded, and trucks drive for a fraction of the true cost of what they run. So that's a whole other subject through there. So passenger train's pretty good. Air travel, we just saw, that's really good miles per gallon. And so you get really good mileage, or number of miles produced per unit of energy, right? So that's great. That's really good. Commuter rail, not quite as good. Well, they're running slower, they're heavier, and they're stopping a lot more. That's going to detract from their efficiency. For that personal automobile, there you go. A truck obviously doesn't get as good mileage. And then a transit bus, which again, a lot of stop and go and a lot of times empty seats. And so by passenger mile, if the bus is half empty, but it's using 3 times more fuel than a car, that's hurting your average, right? So keep that in mind. Here we can compare freight movements the same way. So here we've got cargo capacity versus between shipping on, this is inland waterways in the U.S. This would be like the Ohio River or something, or canals throughout the U.S. And so here's a barge, and they put those together, they lash these together, and they make a 15 barge tow, and then it's got a single tugboat pushing it back here, and off you go, or I think they call it a tender. And so you've got a single tender pushing this, and so that's pretty efficient versus a train, right? So the amount one barge can hold in a 15 barge tow, here's how much one train car handles. Here's what an average length of train would be. This is bushels of grain, so forth. And here's what a semi could handle, right? So a barge is equal to 16 train cars or 70 semis. And a single tow like this is 6 trains worth, or 1,050 semis. So nothing beats the efficiency of traveling by water, really. That is by far the most efficient mode of transportation. For that, you can along the Ohio River, there's a lot of shipping traffic and a lot of aggregates and get sent as well as grain and so forth. And it is really cheap to ship along a waterway like that. So keep that in mind. Here's another graphic. This is from the ports of Cincinnati, northern Kentucky. And you can see that this is how many miles a single ton of freight can be moved with a gallon of fuel. So how many miles, if I had 1 gallon of fuel and 1 ton of freight, how far would that go on each of these systems, right? So shipping by water, I could go 576 miles, right? And by train, 413, and by truck, 155. So just showing you the relative efficiencies of that. Actually, I've seen a more recent number for trains, and it's more in the 450 category these days, right? The trains have gotten a little longer. They have newer engines, the Tier 4 EPA standard engines, so they've become even more efficient for that. Here's pollution, if you're interested in the pollution side of it. This is published by the ports of Cincinnati, so look how great shipping by water is on the river versus train and truck. Right, and this is CO2 production by each. Right, if you want to look by this is pounds of CO2 per passenger mile. So if we're back to equating things by passenger miles, all right, through here, you driving by yourself in an SUV is really bad. And if you're driving in a car, it's a little less bad. Here's airplane, and this is emissions, right, versus bus, Prius. Here's Amtrak, right? Rail transit. So rail transit wasn't as efficient by energy, but it's producing less emissions than Amtrak. It's interesting, right? And so forth and so on. And if you get nearly full passenger cars, 50 passengers, pretty good loading, right? That's really drops for that. Yeah. And then as far as miles per gallon on the road, I've heard van pools, if it's a nearly full 15 passenger van, is one of the most efficient road-based modes of transportation, right, through there. And now emissions for walking and biking are really low. Right, that's great, even better for that. So that's interesting. Airplanes, you might think, but they're really efficient, right? We just read about that. They're really efficient. Boy, they're really polluting too. Well, there is no exhaust. There's no emissions controls on the back end of a jet engine, right? It's just shooting burnt gas straight out the back, right? There is no particulate cleansing. There's no muffler. There's no catalytic converter, and there's nothing back there. It's just shooting jet fuel, which is kerosene. So it's burning kerosene and whatever particulate you've got in kerosene, which is fairly clean. It's much better than diesel fuel. But whatever is in that is coming straight out of the back of the engine. Right? So that's maybe one reason that we have a higher carbon dioxide production per passenger mile for airplanes. Right? And that kind of came, I think, in the last fall, that Greta Thunberg kind of brought attention to how polluting air travel was for the environment. So she sailed across. She came to New York for a talk and sailed here on a sailboat from England, she's from Sweden. So she just sailed across the Atlantic on a sailboat just to exemplify how much carbon dioxide she was saving from the atmosphere by not buying a plane ticket. There you go. Here's tonnage by mile. This is across the U.S. This is probably 2 or 3 years old. I'm trying to remember what year it was. It's not listed on here. So this has changed a little bit. And so the red is tonnage by road, and the blue is the tonnage traveling by water. And so that's the barges we just saw. That would be that. Mississippi is the main corridor for that. And then here's the inland coastal waterway right through there. So that's the main shipping areas through that. And then the green is the railroad shipping. And see, here's the transcontinental route. It's kind of being obliterated a little bit here by I-40, but it's the main transcon route coming out of LA headed for Chicago, and a lot of container traffic, right? That's what comes in LA. It's all the stuff we bought from China. So it's coming in through here and crossing somewhat also on the Burlington Northern route across the top, and also right through here through the center. This is the Union Pacific, I think, line coming across there. Through that. This is the old Santa Fe line. I believe. Do that. So those is, you can kind of guess, okay, those would probably be busy. All right, but what's this big glob out here? All right, why is this by tons the major routes? And then it kind of comes across this way after that and continues on across, right? What is rail hauling out of northeast Wyoming? Well, I'll tell you, what rail's hauling out of northeast Wyoming, it's coal. And that's why I think this graphic is probably a little outdated now, because in the last 2 years, coal consumption, which is almost all for electric power generation, has dropped. Like, I think in 10 years it's dropped by half in the US. I mean, it's a very precipitous drop. And you can see here's locations of all the power plants that were being supplied with coal from the Powder River Basin. That's what this is what this glob we're coming out of here is. And almost all that coal that's mined is put on trains, because trains are super efficient at moving a lot of something in bulk long distance. And that's exactly what this coal production is. Right, it's moving long distance. And you can see where all these power plants are, kind of matches the direction all this train traffic is going. So that was interesting. Unexpected amount of tonnage coming right out of the middle of the country there through that. Then so we're going into, so now we just did our segue, right? So we've done with airlines and we're moving into rail now. And so a little bit of history to get back into rail, or to warm us up for it. I thought this was an interesting piece of history. This is the Union Pacific M10,000 and 10,001. They built two test trains in 1934, right? So it's been a few years, right? That's 90, 4 years ago? No, did the math wrong there. But anyway, it's not quite 100 years ago. So this is the 1934, this thing debuted. And yeah, it looks radical, right? So what is on the rails in 1934? It's all steam locomotives, right, at this point. And diesel locomotives were just getting started. And this was a test one that Union Pacific had built, and to see if it could handle passenger traffic well, and if it was durable, and if diesel was the direction they wanted to go, right? Everything at this point is built using steam locomotives, which could be really fast. I mean, even in the Penn Central line that goes through Valparaiso, they hit speeds out in just to the east of Valpo. They were hitting speeds over 100 miles per hour with the steam locomotives back in the 40s. That was, and regularly, right? It's so flat and straight out there, they could get up to full speed. Right nowadays, we were nowhere near that on track speeds anymore. But and back then, the major moneymaker was the passenger traffic on the rail lines. They did a lot of freight, like, especially early on, almost all the freight and everything that moved was on by trains and on rail. But their moneymaker was passengers. And it's just like the airlines now. The airlines haul a lot of freight as well down in the cargo hold of their planes. But it's the passengers where they're really making their bucks for that. And it was the same. This was, if you wanted to get anywhere, any decent speed, the roads were terrible until about the 30s. They started getting better. But the roads were so terrible, if you want to go anywhere, you're taking trains. That means there's a real definite market for passengers on trains, and that means you could charge more. And so this was where they were making all their money. So having fast passenger service, and they were all in competition, right? So like between New York and Chicago, which is, I guess, one of those lines came through Valpo. It's New York Central versus Penn Central. And that was their bitter competition, is who had the faster train from New York to Chicago and the better route, right? So New York Central was the lakeshore route and the water level route, I think they call it. And that was their marketing trick. I don't know what Penn Central marketed theirs as, but they had 100-mile-an-hour trains. But they had a really straight, boring trip through the center of Indiana. So maybe that was how they marketed it. But that was bitter competition. Those are big cities, and there was a lot of people going between them. So a faster train is awesome. So one that's less maintenance is great, and all that. So they came up with this, and some of this is marketing too, right? If looks like we're a more modern company and we get all this good press about our fancy new train, that's a good thing, right? We're marketing. So this is their train. Through there, they tested out. I'll let you follow that link. In the interest of time, I will not play that now. Plus, it doesn't record well on his screen recording software. But if you look in the notes, you can follow that link. It shows you they had sample video of this first train coming out of the shops and testing up and down the track in there. So you can see it run. You can hear it. It's weird. It's a little weird horn go and on and so forth. So that's so this is the Streamliner, right? And it set the speed record from Los Angeles to New York. They did a publicity stunt. So this is Union Pacific. Union Pacific doesn't have any tracks, I don't think any, east of Chicago. If they do, it's very few. They definitely don't have any tracks going to New York. All right, so they stop. They're mostly from Chicago to the west. And so they had to get permission from one of the other rail lines. It was either New York Central or Penn Central to get all the way to New York. But they tried to do this publicity stunt to show exactly how fast, right? This was a big deal in the newspapers back at the time, showing how fast their train was. So they set a record. They set the land speed record at that time for crossing the country from Los Angeles to New York, 57 hours. Yeah. What do you think about 57 hours? Sound like a lot? I don't know. You ever driven from New York to LA? Take me longer than 57 hours. I think, because I'm going to stop, right, and sleep. The train just keeps going. All right, so that's the speed record. It was the land speed record at the time because there weren't any good roads. Now you can drive. Some of these people try to set records and drive 100 miles an hour. The cannonball run stuff. They can drive faster than that. But it was also setting the record for trains at the time, right? So there's your publicity. We've got this awesome streamlined train, and look, we took it all the way from LA to New York, which is unusual for a single train to go all the way through. You just had to change in Chicago. Is how that works, right? So what's the current record? Right. So in 1934, the Canary Bolt, as they called it, it had a 900 horsepower engine. Get it? It's an as yet unbroken record of 57 hours. Yes, that is true. The fastest speed a train has ever got from LA to New York was in 1934, and it has never been beaten. Right. Sounds like a challenge, right? Should we get it? Let's get a train. Let's Amtrak get out there and try to beat that. Nope. No one's ever beat it. It is still the fastest train trip ever across the country. Isn't that this crazy? 1934. All right. Well, however many years ago that was, because I can't calculate it in my head while I'm talking. It is. I just think that's funny. All right. For that. Here's another interesting piece of this. This is all from Wikipedia. By the way, is that when they put this train into service, then because it's okay, it worked. This train works. We put it into service. It was going from Chicago to Portland, and that reduced the schedule from a 58-hour trip, which is what it used to take a steam train to do that trip, to 40 hours. Right, you saved 18 hours using this diesel electric train set. This new train set, right? And that's the only thing they changed was that train, right? We're just replacing a steam train, right? Steam trains are awesome. They were really cool. But this had, I think, much better acceleration and a better top high-end speed. And honestly, they just take less maintenance. You don't have to stop for you have to stop for fuel, but you don't have to stop for coal and water and all the time. And every time a steam train stops, someone gets out and oils a bunch of stuff on it, right? That wasn't, they didn't have that problem on this one. So saved them a ton of time. And that's, if you're in competition with everybody else trying to make fast trips across between cities, saving 18 hours, man, I'm going to buy a ticket on that train. All right, for that. It was also one of the first fully air-conditioned trains, right? Who thought they had air conditioning in 1934? But they did. So there's a little bit of history. This is what other trains at the time were looking like. Right? And this was considered New York Central's. This is the one going between New York and Chicago. They put this big effort into making that streamlined look, and look how great this is, right? But it's still a steam locomotive in the end. And yeah, it looks pretty cool. It maybe a little less drag on it, but that was the competition versus this guy. And one more point, a 900 horsepower engine is tiny. It's really not much for a train. Current trains are running 5,000 horsepower for a freight train. and 5 to 6,000 is not uncommon, right? So this, and that's actually one of the things they were testing in 1934. There were no really good diesel engines, and so a company called Winton came up with the first diesel, and it was big enough and powerful enough to move a train. That's what really took off then. And so by the mid 1940s, everything was starting to move toward diesel, and by 50s definitely it was, and they started retiring all the steam trains then. So all right, little history there. Here's what it looks like if you were here from Google Maps. If you were to drive it from New York to LA, and I went to the train stations, right, Grand Central to the Union Station in Los Angeles, it would be, if you drove straight through, Google thinks it'll take you 41 hours, right? Okay. So that's by car, not stopping, and that's averaging 68 miles per hour, right? Think about that. That's keeping that thing moving, right? This includes every time you stop for gas and get snacks, right? That would average into that, right? The train average would have been 49 miles per hour if you were on that. But now the train route was a little bit longer, so they actually averaged about 56.5 miles per hour on that. So that's pretty good. No, you can fly faster. It's only $300 right through there. So a little comparison. Here's what the train was nowadays. If you were to take Amtrak, how long would it take you? It would take you 67 hours and 20 minutes by schedule if they arrived on time. And I will tell you, they don't arrive on time. I ride the train fairly often still. I did take this route once to LA from Chicago back when I was a student. And I don't know, we were only 2 hours or 3 hours late, I think. So it was much better than I expected it to be. But you're on there 2 days and 2 nights. It's that train. That is a long time to be on a train. So it's 43 hours. Right? So it's not quite a full 2 days, but it is a lot of time to be on a train and not have a sleeper car. So that's where we're at today. We have not improved on anything since 1934 in trains, right? Some of the things that this train was really cutting edge, right? Now we get all this grief about the U.S. has no good trains, no high-speed trains. Hey, we had the first one. Look at that dog. Some of the things to make trains go faster and ride smoother is you share, they call this a bogie. You share this bogie between 2 cars, right? That was on this train. This train was made out of aluminum. It was much lighter. The ones before this had steel skins on wood frames, a lot of the passenger cars. And then they went to metal frames with still steel skins on it. This one's an all aluminum construction, so it's much lighter. This was a more efficient, easy, more balanced ride, doing all this, sharing that. So there was a lot of stuff that they did debut in that train. That kind of carried on, right? So, moving on to railroads. This is where our current railroad lines are in the U.S., and they broke them down by railroads. And the term we use is Class 1 railroad. A Class 1 railroad are all the big ones. So Norfolk Southern, Union Pacific, CSX, Canadian National, Canadian Pacific, Kansas City Southern, and Burlington Northern Santa Fe. So we have 7 Class 1 railroads, and that's them. Do we have Class 2 railroads? No. They just drove. We don't call anything Class 2. We only have Class 1s. After that, we just call them short lines. And so these short lines are regional railroads, and they're usually 200 or 300 miles long. Is about the max, and they feed into these Class 1s. All right, and so you can see the routes. Like here's the Burlington Northern Santa Fe. That was one of these major transcontinental routes we saw. Here's Union Pacific's coming up this way through Salt Lake City and across. This was the original transcontinental line through here. It's still being operated by Union Pacific through that. And then Burlington Northern also operates what used to be the Great Northern Line across northern Montana. That was the other transcontinental route from Chicago to Seattle through there. Norfolk Southern and CSX operate in the eastern U.S. Right. There's a little bit of crossing here up around us in Illinois, but it's really kind of the Mississippi or Chicago, whichever way you look at it, it's kind of the dividing line. So there's the 2 main eastern railroads, and everybody else is more of a western railroad. Amtrak only has its own track between Washington, D.C. and Boston. Parts of that are owned by Amtrak, and that's really it. They may have a little some miles here and there scattered around. They have some track in their own yard in Chicago, for instance, and probably also in LA, but they don't have any long distance routes that they own. They actually, all their trains are operated on the class ones. And so that is one of the reasons why it takes so long getting anywhere on Amtrak is you're often waiting on freight trains, right? The passenger trains are still supposed to have priority, but if you're stuck behind a 50 mile per hour freight train, you're just stuck behind it, right? Until it can find a siding and pull over and let you pass through that. There's other reasons Amtrak's late. Some of it is that freight operations is, I think, one of their leading causes of being late. And they're pretty good at being late. Kind of known for it. They've actually gotten better, I've got to say. In the last 10 years, they've gotten better for that on most of their rail trips for that. So how design? How do you design for a railroad? Well, it's a weird thing, right? And we were the stuff we've looked at in our book is written by Association of State Highway Agencies, AASHTO, and they write the Green Book, and that's what that stuff comes from. And it's a recommended practice. And railroads are being privately owned. It's up to the individual company what they want their standards to be within reason. Right. Now they have a similar organization to AASHTO, and they call theirs a REMA, and that's the Industries Association. And then we have REMA manuals, and they tell you how to design rail stuff. But each major railroad, and it's usually this the class ones, have a tweak on that, right? And okay, well, yeah, REMA says to do it this way, but we prefer, add this to it as well, because that's how we do it. And we own this railroad, and we can do what we want, right? Now they are inspected and checked out by the Federal Railroad Administration. So there are roving FRA inspectors who will come and inspect the railroads, make sure they're safe and they're doing things by the federal standards. But there's a lot of leeway still for them to make their own choices and how they want to do it. So here's the book, and Norfolk Southern says, well, if you want to build an industrial siding that connects to our railroad, here's how you have to do it. Here's what we're going to ask you to do. All right. And we did work for them once in consulting. They sent us their design standards and their manuals. And it's not far off for REMA, but they have their own way of doing certain things. And that's how their entire line is done, based on that. So keep that in mind. We looked at typical sections of roads, and so we can do the same thing with railroad now. And obviously the rail is probably the most identifiable part, right, of a track structure through that. And we will align up, we'll do our alignment down the center of the track. That kind of makes sense. The profile grade, remember on a road, it's at the center line, at the peak of the road in the center is what our profile grade is. When you design your vertical profiles, that's the point in this typical that you'd be pointing at. In railroads, it's at the top of rail elevation, right in the center for that. So we measure everything off the top of rail in that. And then below that, this is our tie, the wood ties typically, but it could be other materials as well. So that's our tie. And then below that, we've got ballast, which is the large rock. It's usually 1.5, 2-inch diameter type rock, nominal. And that's the ballast. And then below that's a sub-ballast, which could be different kinds of rock, in .53 sometimes. For that, or whatever that railroad standard told you it should be. And then you finally have the soil, the natural soil, the subgrade down below that. All right, for that. So this would be a typical section for a railroad track. Also, in highways, we talk all about pavement. Well, this is the equivalent of pavement, right, in trains, which is the rail, the actual rail itself the train runs on. So we're going to kind of work through this typical section from top down, and then we're going to talk about some geometry next time on this. So this would be typical rail that we would have going through here, and it is in pavements we talk about how many inches deep is this pavement, right? We calculated that. We know how to do easels now and all that. In railroads, it is they do rail by poundage, and that is how many pounds per yard that's this piece of rail, this section weighs, this cross section of rail weighs. If you form this at the steel mill and it comes out right, you've probably seen pictures of it rolling out in long strings of this rail. every yard of that will weigh, so many pounds. And it depends on the shape. Here's a bigger rail, stronger rail, and it's going to have more material per yard in it, so it's going to weigh more. Right? The steel is going to weigh more for that. And these are the common sizes now: 115, 136, 141 pound. Yeah, in the old days it was more like 80-pound rail, but it's gotten heavier over time. And this heavier, larger rail, the reason they've moved to this is it allows you to carry heavier loads, right? You can put more weight on a single cargo car coming across. Whatever it's hauling, it can handle more weight. So you can use bigger cars, rail cars, on that, right? And so you've got more volume. Also, it can handle more trains. It can handle higher speeds, and it can resist the forces that occur during sharp curves and high grades on that. So it's just all around a beefier rail, stronger and better for all these things, right? Heavier, high use areas and heavier loadings. That's good for that. And this 136, 141, these have become the standard. 115 is becoming not so much common anymore through there. And then we'll do one more thing to finish off today in talking about rail, and that is, this is what the contact area, which I think is kind of an interesting picture. That steel wheel of the train car riding on the rail, the area it's actually in contact with that rail is only about a half square inch, 0.5 inches squared. And so it's like the size of a dime, right? That is a very small area. And these are really heavy cars, right? Rail car, the max loading on most Class 1 mainline is 286,000 pounds. And that is spread over eight wheels. Right, so 286,000 pounds divided by 8. Okay, whatever that is. I'm not apparently good at math anymore, so I'll let you guys figure that out. All of that weight is right here, right? And that is why we also harden rail. The heads of rail will often harden it because if a heavily loaded rail car just sits here too long on a non-hardened rail, it will deform. It'll just slowly kind of deform that rail, and it puts little divots in it, which then you feel when you ride across it, and it causes trouble. And you have to eventually grind the top of the rail off and reshape it for that. So I just think that's interesting. That's how small that space is, or that area is, that this wheel sits on. It's really impressive weight, right? That's a lot of weight on the head of that rail coming through there. So anyway, I think that's interesting. Next time we're going to pick up, so that's a little bit of the track structure piece. Next time we're going to talk a little bit more about track and some of the geometrics of how rail differs from roads.